Junbo. I'm going to talk about my selected paper. The name of the paper is Divide and Conquer Meets Consensus, Unleashing the Power of Functions in Code Generation. So, a brief introduction about it. So, this is much remarkable progress in LLM this year, and see its application into realm of code generation. But here we face some problems when it comes to more complex requirements in code generation. The solution provided by those LLM are usually flawed. So there are some existing solutions to solve this problem. So for example, plan and solve, multi-agent frameworks, and also self-improvement methods. But each of them are having some limitations, and let's talk about this. So for the plan solve decomposition, it requires you to plan everything ahead. So before you implement, you need to have a integrated plan about how you design the function, what's the return value, what is there any if then condition, and everything you need to consider before you actually implement it. So when the LM try to implement it, it's hard to change its high level idea. It's hard to adjust some parts of the plan. So it is lacking the adaptability. And for the second approach, multi-agent collaboration, you are like try to assign different roles to different models, and they all work together like a group of workers in a workflow to generate the final results. But this process relies heavily on the LLM capabilities. So different models have different capabilities. So this method is really hard to generalize to different models, especially the small scale models. And for the third approach, it is self-improvement via the self-tests. So this method depends heavily on the correctness of generated unit tests, but from some preliminary research on this paper, the unit tests generated by models are usually flawed. So the final result may actually contain some mistakes. So the program is not work, but it passed all the tests generated by the models. So here the paper introduced their own approach, which called funcoder. So the core idea is just combining divide and conquer strategy with their design functional consensus to improve the code generation. And how it works, so it just recursively decomposes the complex problems into sub-functions. And when you solve those sub-functions, you aggregate them together and select the best among those different implementations through the metric of functional consensus. So from this diagram, we have the initial requirements, the function signature with some descriptions probably, and you divide it into sub functions G and H, and you use funcoder to solve those sub functions, and you get desired sub function G star and H star, and you put it back, aggregate back to the parent function. Here you may have different implementations when you try to sum up the parent function. So we have a group of sample implementations, and with some generating possible inputs, we tap into those sample implementations, and through the metric of functional consensus, we finally find a best function among those samples, and we return this best function as our result. And here you see the red diagram. This is a pseudocode for the funcoder procedure. We first divide, we extract a group of sub-functions from the original function signature. So here you see if a component is not implemented, we recursively use the procedure to find the sub-functions, and we add the new sub-functions into as a child of the parent function. And in the conquer stage, we try to sampling the parent function with its child, and so we have those sample implementations, and through the functional consensus part, we are finding the best among them and finally return it. And in the right part of this diagram, so in original plan-based composition, we need to create a function, generate sequence, check if then, return everything we plan ahead, and then we generate the code. But in this funcoder strategy, we decompose through coding. So we first write our current function and introduce new function. And when decomposition and the new functions are left unimplemented, but it still works. Yeah, and we are generating a hierarchical structures through the procedure. And let's talk more about the functional consensus. So firstly, why is it needed? So it is preventing cascading errors from propagating through sub-functions from bottom to up. So one problem of those plan ahead decomposition is that if there's some error in your some part of your plan, so the errors will propagate into back to the main functions after when the implementation. But the function consensus strategy is here to prevent it. So how it works? So it samples multiple function implementation, different version of implementation, and it select one of it as the best through the highest behavioral similarity, this metric. So the metric is just like this. There are some mathematical formulation about it. So it's just when you have like a domain of generated inputs, and you compare to different implementations F and G. So the similarity score between these two functions is just how many outputs they generated are the same, given the same input. So if the similarity score will be 1 if all the outputs are generated same for both F and G, given same input. And here, consensus is reached by selecting the candidate F star holding maximal similarity with all others after sampling multiple function implementations for the same requirements. So you can see from this formula, if a function have sum of similarity to others for every function other than it in the sample, we know it is have similar behavior to all others in the sample. We know it is the function consensus we want, and we will try to output this function into as the result of our funcoder. And let's talk about more details about the two stages. So for the divide stage, we instruct model to write the current function and introduce new functions with clearly defined sub-goals. And the paper provide us a sample of the prompt for the divide stage. So the two key parts is underlined and started here. So we need to include some words like you can decompose it into multiple smaller functions when we ask the LM to generate function, and we also want the LM to leave some new function unimplemented for now, a write function at the end of the code and comment what the function does. And we can continue this process, repeat this process to build a hierarchical structure. And for the conquer stage, we apply the composition of subfunctions to write the parent function after all subfunctions have been fully decomposed. And the functional consensus is applied in the conquer stage. So a sample prompt for the conquer for the start sentence. Consider reusing existing functions that are already implemented, and you can import libraries to better solve the problem. So in the conquer stage, be reusing those solved functions and to implement our parent function. There can be different versions of this parent function implemented, and we group all those different versions into sample implementations and finally apply this functional consensus strategy to find the best one and return the result. The paper also do some experiments to test the efficiency of the funcoder strategy. The benchmark used are human evaluation, MBPP, and also Xcode evaluation. So these three benchmarks is just different code generation tasks, and we compare our funcoder strategy with those traditional method and some previously mentioned new approach to solve the complexity of the code generation. So there are standard prompting, two-stage decomposition method, self-testing, self-improvement method, and multi-agent developing framework. So from this diagram, we can see all the bold numbers are the best score among different experiments, different round of experiments. So as we can see, funcoder in the most case are outperform all other methods. It has the best performance in different setup. Yeah, when we are using different models, not only those large models, but also some open source small models. And the paper also set some experiments on math performance, on math part. So here is a competition level mathematical reasoning benchmark. It is divided into different subjects such as pre-algebra, number theory, counting, etc., etc. And the methods are divided into two categories. The first one is test-based baseline, and there are standard prompting chain of thought. And the second category is program-added baseline. There are program thought, self-refined, and cumulative reasoning. And our funcoder is one of the program-added baselines. As you can see, same here. We see funcoder is usually the best, usually have the best performance in different set of the experiments. So we want to make some analysis on funcoder. So why the funcoder works better? So the paper mentioned it avoids planning constraints and reducing the complexity of reasoning. So because we are decomposing our original requirements along the way, so we are not planning everything ahead, and because we divide it into two smaller and simpler functions, sub-functions, we are reducing the complexity of the requirements. And also, the funcoder can handle error better than self-testing. And this from the preliminary study results. So here you see this diagram. So through self-testing, there are some results conducted by the paper, conducted by the author. So we can see 25% for GPT 3.5 and 16.5% for this stable code model, which is an open source model. So when we are using self-testing approach, about 20% unit situation that the unit tests produced by the models are actually wrong. So sometimes our program generated by the model is actually correct. These are filtered out by those wrong unit tests. So we know that the self-testing from the models are usually unreliable. And we also, for some small models, the final field metric means the program is actually wrong, but it passed all the tests generated by the language model. So which means the tests generated by the models are not that reliable. It cannot find some error in our program, and if the program passes all the tests, it regards the program as valid program, but it's not actually working. So through the functional consensus, we can avoid this thing happen. We can elevate this situation. We handle errors better than self-testing, and it is more adaptable to smaller models because we are handling some simpler requirements, some decomposed requirements each time, and it is more friendly to the smaller models. And for the paper also done some evaluation study. It found Funcoder significantly improved the performance with minimal extra computation cost. So here in the diagram, you see with divide, conquer, and ranking strategy implemented in the Funcoder, we have about 20% increase in the pass at 1 metric, and the average token does not increase that much with this improvement in performance. So the pass at 1 metric is just the very first generated result pass all the tests. It means this. Yeah. It is metric describe this sentence. And so let's discuss more about this strategy and some further work about it. So the limitations a Funcoder is mentioned in this paper are it focuses on more competitive programming and structured code generation. Because through the divide and conquer, we can decompose complex requirements into simpler one, and we also have seen the somewhat strict prompt requirements in that I mentioned before. So you need to include some specific prompts to let the LLM do the correct thing to actually process the procedure of Funcoder. So more structured, a more complex, a more formal code generation task is more fitted into this strategy. And so this may not generalize well to some open-ended and not formal software development tasks. And some future direction of this strategy is just to expanding the function coder to more complex software engineering use cases. Not only code generation, but also some other tasks that could share the procedure of the Funcoder. So in conclusion, so the key takeaways of Funcoder is that it enhances LLM-based code generation with divide and conquer, and the functional consensus strategy help to improve the reliability by selecting the most consistent implementations with others. And we can see it outperforms all those existing approaches, and it works better in those smaller models. And the funcoder paves the way for more structured and accurate code generation. That's all for my presentation, and here are some questions to think of. So I list some of it, and you can think about others. So how does funcoder compare to multi-agent systems for code generation? So which approach you think are more scalable? And also, could there be cases where the consensus-based selection that function coder has fails? And that's all for my presentation, and thank you for watching.